I'm sharing.
Okay, we see that.
Yeah.
Thank you very much. The floor is yours.
Okay. Thank you for the invitation. And thank you, Alex, that make my life easier. Already making some propaganda. So today I'm going to talk about mainly these two papers. The first one in collaboration with Gauthier, that's focused on massless particles. And the second one in collaboration with Gauthier, Tepe, Yael, and Yanif, that is then focused on massive particles. So very shortly, I would say that the idea behind this amplitude program is to actually avoid Lagrangians and the redundancies that are coming from gauge symmetries. And instead, the idea is to work directly with on-shell amplitudes. So in particular, the amplitude methods were pushed by the necessity of having more precise calculations for process contributing to the collider background. And in the past decades, not only processes with many loops and many external legs were computed, but also new insights and hidden mathematical structures were found. So Alex talked a little bit about the graviton case, for example. So the question that I have been thinking in the past years is like, can we expect also to find more efficient methods and at the same time have these new insights when we look not to the background process, but looking to beyond standard model process using these on-shell methods? And to be more concrete, we know that the nature is making our life really hard, and it seems unlikely that a big bump will appear. And looking to indirect surds and parameterizing any deviation from the standard model coming from heavy new physics using the HEFT approach is very useful. And indeed, what we have been seeing lately is that what is allowed for deviations gets smaller and smaller, which then means that we need sometimes to go beyond the dimension 6 analysis and also look at process with more legs and more loops. Moreover, recently there was a lot of discussions on how to differentiate linear and nonlinear realization of the lattice symmetry. And the way to go seems to look at process with several vector Boswell's legs, which can be also challenged to compute in the usual way. So, I mean, looking at this picture, it seems that thinking about on-shell amplitude methods in the context of the standard model HEFT can actually be a good idea. So the first step is to actually define the equivalent to this MEFT or HEFT in the on-shell way. And note that here the idea is to do it without a Lagrangian and just writing the on-shell 3-point, 4-point, 5-point amplitudes, just using some simple rules as Lorentz symmetries, locality, and unitarity. And actually, the SU2 cross U1 can be imposed demanding perturbative unitarity in the 222 process. And here it's not even necessary to choose between a linear or non-linear realization. So the 3-point amplitudes were already studied in these two previous works. And here I'm going to discuss the next step, that is to build actually the 4-point contact terms. So the plan is pretty simple. I will just give a quick spinor review and talk about the difference between the massive and massless spinors. And also, then next I'm going to talk about the massless contact terms, move to the massive case, and just end up with some conclusions. So using spinor variables to describe amplitudes has the advantage to make transparent the Liouville group transformation and make clear how the Lorentz symmetry constrains the functional form of the amplitudes. And for massless particles, the Liouville group is U1, and we can decompose the momenta in a pair of spinors. And I mean, if you're not so familiar with this notation, just remember that these angle brackets times square brackets are related with the Mandelstam variables. And also that angle brackets are associated with minus half helicity and square brackets with plus 1/2 helicity. Now, moving to the massive case, I'm going to be using the formalism of Arcani, Hamed, Huang, and Huang. And here the Lero group is not U1 anymore, it's SU2, which means that we need 2 pairs of spinors to describe the massive momentum, where this I and J are the SU2 indices. And of course, now here the determinant of P is M square. And also the polarization tensor can be Ricking symmetrizing over the Lero group indices. And also that in this formalism, we don't need to choose a spin quantization axis a priori. And this is one of the biggest advantage. We can work with this massive Lero group in a covariant way. And I'll be using what's called the bold notation for massive spinors, where I will often omit this SU2 index and symmetrization when doing so. So something very useful here is that the high energy limit nicely connects the massive and massless spinors. And just to show, these are the explicit form of these massive spinors for this momentum parametrization here. And going to the high energy limit in practice means that we simply need to unbold the spinors to get the leading term in the high energy limit, like this one that it's here. And so to explain a bit better why this high energy limit is equal to this unbold, we can thinking about decomposing the massive momenta into 2 momenta such that they scale as energy or as m squared over E. And in terms of spinors, this means that we are taking each component and decomposing into 2 pairs of massless spinors such that this relation here is valid. So there is not a unique way to do this decomposition, but with this choice here, we get that at leading order, the bold square spinor goes simply to unbold square spinors and similar to the angle brackets. So it's very easy to see what's the leading term in the high energy limit. Now, to be more concrete, let's just look to some examples. And remember that the massless square bracket is basically half helicity. So the Lero group for the plus 1/2 plus 1/2 scalar fix the amplitude to be simply this 1, 2 square. And since the mass dimension of a 3-point amplitude is 1, we have just a dimensionless coupling in front. And for the plus 1 plus 1 plus 1 amplitude, we need 2 square brackets for each particle, which leads to this combination 1, 2, 2, 3, 3, 1. And the mass dimension required, we divide the amplitude by a mass scale square. And this is what we map with the F cube operator. So moving to a 3-point amplitude with massive particles, the SU2 Lero group allow us to have 3 possibilities. And the first term is normalized by M, because indeed, when we go to the high energy limit and on both the spinors, we have the process with the longitudinal modes. And the other 2 terms lead to the amplitude with the transverse modes. So this is just a glimpse of how amplitudes can be useful to systematically build and count these higher dimensional operators. But I just want to mention that indeed the problem of constructing bases of operators had a huge development in the past years. And there are many different approaches that can be more practical depending on the application. So to start with the massless case, the idea is that the operators are in 1-to-1 correspondence with non-factorizable or contact amplitudes. And this can be in general written as a minimum spinor structure times a function that's it's Lero group neutral and is just made of powers of Mandelstam variables. So in this paper with Gauthier, we focus on building these minimum spinor structures. And what we notice is that we can just count the number of square brackets and angle brackets required by the Lero group. And if the number basically doesn't match, this means that we need to include the momentum insertions. So this basically is determining what is the minimum operator dimension, just looking by the listed configuration, which leads to this general formula here. So the nice feature is that we found a very simple procedure that allowed us to build spinor structures corresponding to the SMEFT operators up to dimension 8, and also to the GR SMEFT, which includes all operators with gravitons. Now, I told you that to go from massive to massless, we can simply unbold the spinors. And I told you that we have a procedure to build the massless contact terms. So the natural question is like, can we now just bold what we already found? So it doesn't seem like a bad idea. So let's try. So let's build a contact term for 2 fermions and 2 scalars. So looking the massless amplitudes, we can have fermions with same helicity or opposite helicity. And notice that, as I said before, they arise at different dimensions. So, and I can also write, of course, the permutations of these 2 amplitudes. So far so good. And now we just bold everything. We can write this 2 bolded terms and also the permutations, where each term comes with a Wilson coefficient that I'm not writing here. And indeed, one can check that indeed this corresponds to this kind of minimal structure, because we can now simply multiply it by powers of Mandelstam variables to get operators of higher dimension. So far so good. Let's keep this game and look to 2 vectors and 2 scalars. And now in the massless amplitudes, we have also to consider the ones corresponding to the longitudinal modes. And again, you can see that the operators arise at different dimensions due to the different listed structures. Okay, so let's just bold it. Again, we can check if this corresponds to the minimal spinor structure. And here we actually find a problem. So at the massless level, we can write some trivial identities like this one. And this actually leads to a question. Is there some massive identity that can relate spinor structures once I multiply them by Mandelstam variables? It turns out that the answer is yes, there are non-trivial massive identities like this one here. And this means that this type of combination should not appear in this minimal spinor structure set. In principle, most of the time, we can simply check if 2 massive structures coincide in the massless limit, and the exact form of these identities is not needed. However, Gonstall modes are normalized by M, as I showed in the 3-point case. And this means that knowing the powers of M that can appear in the denominators is important to analyze what is the dimension of a certain operator. And this analysis is important as in the HEFT basis, we want to keep the lower dimension operators and not trade one of lower dimension for one of higher dimension. So this motivates us to define a different type of basis. So the first one, we have the spinor structure basis. This is basically what gets bolding these massless spinor structures. And indeed, this is coming just from the Lero group structure. And also this is equivalent to the counting of correlators in a conformal field theory in 3 dimensions. Or we can also just count, do the counting, thinking about gluing 3-point amplitudes with a mediator of spin S. So next we have this stripped contact term basis. And here we want to take into account these massive identities and also keep track that the longitudinal modes are normalized by masses. And as I said, this is important to count the operator dimensions and not trade operators of lower dimensions for ones of higher dimensions. And now once we have this stripped contact term basis, we can simply multiply it by powers of Sij to get higher order operators. So this is part of the table that contains the 4-point massive contact terms. The NES counts the number of spinor structures, and the NES-CT the number after removing combinations to the massive identities. So note that in the FFSS case, both sets are equivalent. And however, in the VVSS, there is this one specific combination that I showed that appeared to this massive identity where it should be removed. So in the end of the day, we present a list with all 3-point massive amplitudes with spin smaller or equal 3, and all 4-point massive amplitudes with spin smaller than 1. And just one more comment about the massive identities. In the case of the 3-point amplitudes, we have this identity here in the first line that appears when writing the massive amplitude of 3 vectors. And looking amplitudes with particles with spin up to 3, we found that any other identity that can reduce the number of independent spinor structures is kind of derived from this one. And moving to 4 points, this situation gets considerably more complicated. And in particular, this first identity here cannot a priori be guessed looking at the massless limit. But anyway, we listed all identities found, which can be useful not only for these base constructions, but also for general manipulations involving these massive spinors. Now, the contact terms that we present are completely general. And in the paper, we also discussed the structure for the electric particle content. And I'm just showing you one example here. This is the VSSS case, which corresponds to the Z and 3 Higgs amplitude. And now you have to see how this works with Bose symmetry. And this forbids a dimension 5 structure, and the next one appears at dimension 7. And you can work out polynomials of Mandelstam variables that are antisymmetric. And this allows to build even a dimension 13 contactor. So this leads me to my conclusion. I hope that I made clear that there are advantages using what is this in this amplitude toolbox. We work out the first step towards the direction of having an on-shell HEFT, which is building contact terms using the spinor variables. And we don't want only to have the massless, but also the massive case. And with our big table, it's possible to compute the 2-2-2 scattering process in this on-shell way. And here, there's the advantage that we don't need to choose between a linear or nonlinear realization of the SU2 cross U1 symmetry. And I mean, as a side note, I also want to point out that the advantage of this formalism go beyond collider physics. And recently, these contact terms with massive particles were also used in the context of computing tidal effects in the gravitational potential. So just to end also with some propaganda, there is a very exciting direction. And we already saw many examples where the on-shell methods were helpful. I told you about these basic constructions, but also using recursion relations to build higher point amplitudes and study soft theorems, or to study loops, as Alex discussed. There are really nice features about using this on-shell method to study this method of anomalous dimensional metrics. Moreover, these amplitudes techniques can be helpful to study massive higher spin particles, as we can completely bypass the Lagrangian construction, which is challenging in this case. So we can also add this to our kind of model building toolbox. So this is that I want to say. Thank you very much.
Thank you, Camila. Are there questions? First again from the room.
Yes, there's one. Hi, I have one question. So you talk about this contact term up to 4 point, right? So I just want to make sure, so I understand that whether you also have a systematical construction of a contact term more than 4 point, I mean, more than 4 particle.
So in the way that we did this construction, I mean, it's somehow systematic, but finding this massive identity is not necessarily easy. So indeed, going to 5 points can be challenging in doing this procedure that we did. But was a recent paper that have some new techniques involved this young tableaus that construct a kind of this higher point amplitudes that I think, I mean, there's a lot of quick development in this direction. So
Sure,
I don't know. Yeah.
Sure. Okay, thanks. So I just want to make sure. So in more than 4 points, so what's the mean difficulty? For example, in the 5 point or 6 point, what's the mean difficulty to prevent a systematical construction?
So in the way that we did is really finding these massive identities. They are not necessarily easy to find.
Okay, thank you.
I don't see any other questions.
Okay, let's see if there are any questions online. It doesn't seem so. So let's thank Camila again and all the speakers of this session. And we close it here for this afternoon session. There is one more session in the local evening in something like 4 hours, if I'm not mistaken. Do the local organizer want to say anything? Any announcement?
I guess not.
Okay. We can still chat if anyone wants in the Wonder Room, and I'll post the link again here. And for the rest, we see you all in the next session. See you. Bye.
Thanks, Gutiérrez. See you.
Thank you, Jane.